Hello, I'm Eric Severson, and I'm going to be talking about time-optimal self-stabilizing leader election in population protocols. This is joint work with John Berman, Thomas Nowak, Dave Doty, Ho-Lin Chen, Shui-Ping Chen, and Sean Zhu. The population protocols model describes a system of agents that update by successive random pairwise interactions. So a scheduler picks a pair of agents to interact, and then some transition rule determines how they'll update. So in this case, two L's meet, one becomes an F, and all other interactions are null. There's no change. The model was originally motivated by mobile sensor networks, but has since become better motivated by chemical reaction networks, where this gives the dynamics of well-mixed solutions. Protocols have also been considered in separate literature of social networks. The leader election problem is a very important distributed computing primitive, where there's going to be a subset of leader states, and the goal is to reach a configuration with a single leader agent, and that leader status should be stable, so it should be impossible to change in future interactions. Now, the original version of the leader election problem, all agents start in some initial state, and we need to converge with probability 1 to a stable leader. So this two-state protocol actually solves leader election, where the initial configuration is all L's, all leaders, and we'll eventually reach a terminal configuration with only a single leader left. Now, in thinking about protocol complexity, there's a notion of state complexity. So here we only have two states or a single bit of memory, which is the smallest possible, and a notion of time complexity. For that, we need to think about how many interactions this random process will take on average. Now, the time is actually dominated by the final transition, where there's two L's left that need to meet. So this transition will have probability 1 over n choose 2, taking an expected order n squared interactions to converge. Now, time is often measured in parallel time, which is n interactions per 1 unit of time. So we would call this linear time. And that comes from the idea that it's order n interactions per agent on average. So this is linear time, and there's actually a lower bound that for any constant state protocol, it provably needs linear time. So you can't do any better than this protocol with only a constant number of states. That lower bound turns out to be generalizable, and it holds up to 1/2 log n states. But then once the state set can be as big as log n, it turns out that you can solve it in optimal order log n time. Now, for the population protocol model, log n time is actually optimal for any non-trivial problem by a coupon collector argument, because it takes order log n time, or n log n interactions, just for all agents to have a single interaction. Now, our work concerns the self-stabilizing variant of leader election. So now the protocol will have to start from an arbitrary initial configuration. Now, this simple protocol with only two states is now going to fail. Why is it going to fail? Well, it could have to start from a configuration with all followers, all Fs. Now, this arbitrary initial configuration is a model of volatile memory corruption. So we would like a protocol that from any amount of memory corruption, starting from any faulty memory, is able to recover and self-stabilize to the correct configuration. There's an immediate impossibility result that you can state for this problem, which shows that if you can solve this problem, your solution, your protocol, provably must depend on the exact population size n. And here's the argument. If you're solving self-stabilizing leader election, then you need to be able to stabilize to a configuration with n agents and a single leader. Whatever protocol works for this population of n agents can't possibly work for a configuration of n-1 agents, because this configuration, excluding a leader, is a configuration with n-1 agents, and it provably has no way to create a leader, because if it did, this original configuration would not be stable. So if you can solve this problem, your solution has to be what we call non-uniform and have the number n sort of baked into the protocol. Also, you provably need at least n states, but once you have an n state protocol that depends on n, this problem actually is solvable. And the simplest solution comes from this paper, and the state set can be thought of as the integers mod n, and the leader state is 0, and the only non-null interactions are when two agents meet in the same state, one of them increments mod n. So for example, here we have n equals 7, and we have an arbitrary initial configuration, so our state set is 0 through 6, and what will happen is eventually two agents will meet in the same state, one of them will increment. This will continue happening until we eventually reach the unique terminal configuration. Now, this protocol actually also solves a strictly harder problem in leader election. It solves ranking, because once we reach the terminal configuration, we can think of these states as assigning the ranks 1 through n. So the agents now have unique identifiers, and also the whole set of identifiers is fixed. It's the ranks 1 through n. And this protocol has another nice property of being silent, where now the only transitions once we get to a terminal configuration are null. So there's no further transitions possible. Now let's think about how long this protocol takes to converge. And there's a simple configuration, which is a good lower bound for how long this protocol is going to take. And it's a configuration that has successive bottlenecks. So we have no one in state 0, so no leader left, and then 2 agents in state 1, and then all other states have a single agent. Now, this is going to take linear time for these 2 1s to meet, then linear time for the 2 2s, and so on. And in total, this will take order n squared time. Now, our work gives time-space trade-offs for this self-stabilizing leader election protocol. So we build, rather than this existing protocol, which takes order n squared time, we have both a quadratic improvement, and then we have a time-optimal solution. So our first protocol we're going to discuss is a silent protocol that takes linear time and uses linear states. We also have a faster protocol, which is not silent, which has optimal order log n time, but uses exponential states. And both of our protocols actually also solve this same ranking problem. So they solve a strictly harder problem in leader election in that they actually also rank the entire population of agents. Now, for our first protocol, which is silent, it's worth realizing that linear time is actually a lower bound for all silent protocols. And the argument is, if you can solve self-stabilizing leader election and you have a silent configuration when you've stabilized, then you could have an initial configuration where you take the silent configuration and you replace a single other agent by the leader state. Now, in this configuration, there's only one non-null transition, the 2 leaders meeting, because every other interaction is also possible here, so it has to be null. And if this is the only transition that can advance the configuration, that's going to take linear time. So you provably have to wait for these linear time bottlenecks if you're going to be silent. So our optimal silent protocol is going to take linear time. And the way it works is the agents are going to have 3 different roles: settled, unsettled, and resetting. The idea is the settled agents are going to have the same ranks 1 through n. And the unsettled agents are going to get their ranks from the settled agents. Now, we would like to reach the silent stable configuration where all agents are settled and have the full ranks 1 through n. And we're going to get there by moving through a reset mechanism. And there's 2 ways to trigger a reset. One is 2 settled agents have the same rank. So if there's any rank collisions, we'll detect that. Or the unsettled agents have a counter up to a linear number of interactions. So either of these will, in linear time, detect an error and move us through the resetting phase. The resetting phase uses a subroutine with a reset counter. And the reset counter updates by taking the maximum of the 2 counters, but then subtracting 1. And to trigger the reset, some agent's going to set their reset counter to a large value, which is on the order of log n. So here, some agent has triggered a reset, they become green. And then when 10 meets 0, they both become 9. If 9 meets 0, they both become 8. And this eventually, this positive signal of green will spread in order log n time to make all agents reset. Then also in log n time, it'll decay back to 0. So this is a logarithmic time resetting protocol. Then for this protocol, we wait an additional linear time to do the slow 2-state leader election. So we have an additional counter up to order n. Then when we have a single leader, when the agents go back to the main part of the protocol, the followers become unsettled and the leader becomes settled with rank 1. The remaining part of the protocol has this rank 1 leader be the root of a binary tree. So we do ranking by a binary tree, where the rule is every settled agent with rank I is going to settle up to 2 more agents. So here we have agent 3 should have 2 children. So when they meet an unsettled agent, that will become their child 7. And we prove that this takes order n time with constant probability to stabilize to all ranks being full. So in total, we have a linear time protocol because it takes linear time to trigger the reset, linear time for the slow leader election during the resetting phase, and then linear time to finish the ranking and stabilize. And it also uses linear states, where the 3 different roles each use linear states, which sum up to linear states in total. Now, our second protocol moves beyond linear time. So it's sublinear time and actually becomes time optimal. Now, the basic idea for this protocol is the agents are going to be either collecting or resetting. So the basic strategy is with these collecting agents, where they have a name from a set of up to n cubed possible names, and a roster where they collect all the names they've seen in the population. So here we have a set of agents, and if the agents have unique names, this protocol is going to quickly reach ranking. And the way it does that is the rosters are going to share all the names that have been seen. So when two agents meet, they're going to merge their rosters. And that's going to eventually lead to all rosters be complete in log n time. It's actually a very quick process for this complete information to be shared. And once an agent has a full roster of size n, their rank is simply the order of their own name in the roster. So now if the agents all have unique names and we were able to be initialized and had no fake names, this would quickly get everyone to have the correct unique ranks. And that would reach this stable configuration where you have unique names and correct rosters. Now, the problem is our adversarial initial conditions could be wrong. So we need a way to detect errors. And then after detecting errors, we're going to use the same reset mechanism. So if we detect any errors, we're going to use the same reset rule, which again takes only log n time to spread a reset signal and get everyone to reset. And then everyone's going to decay back to 0. Then we're going to wait an additional log n time and generate bits for a new name. And then once we have a new name, each agent will become collecting and they'll have a random name from this set of total names. So this reset rule is going to take log n time. And with high probability, the set of names will be unique because we have order n cubed total names. And once we have unique names, we'll get to a stable ranking in only log n time. So the remaining problem we need to solve is how to detect these errors from any initial configuration. Because again, we don't get to assume that we're initialized. We have to consider any possible adversarial initial condition and show that we recover from any possible configuration. So there's two main types of errors that we need to worry about. The first is there could be these ghost names. There could be names in the roster that actually belong to no agent whatsoever. Now, if there's ghost names, but all agents have unique names, then the total number of names in the population will be bigger than n. So we can simply detect when a roster size is ever bigger than n, we know that has to be an error. Now, there's another type of error that could come, which would be there could be name collisions. You could have two agents with the same name. Now, we saw this same type of error in our first protocol, where we simply detected it by a direct interaction. But that direct detection takes linear time. Importantly, though, detecting these name collisions is actually the only slow bottleneck that we have in this whole protocol. So now the key step that we need to solve is how do we do name collision in sublinear time, ideally in optimal logarithmic time. And we need this name collision to be stable and safe, though. There should not be false positives or false negatives. So the basic idea of our faster name collision can be shown through an example which takes order square root of n time. So now again, the direct interaction to detect the name collision takes linear time. But something that we can achieve in square root of n time is to have one intermediate agent. So we have two agents with the same name, both 4. And in square root of n time, some intermediate agent will interact with both agents. And that'll be sort of a length 2 causal path from one to the other. Now, our name collision detection is going to use this idea to detect a collision. So we'd like somehow this agent number 7 should be able to distinguish between the two agents marked 4. The way that we do that is in every single interaction, the agents are going to pick a new random sync value. And this is going to keep happening. So this sync value is why this protocol is no longer going to be silent. And what they're going to do is they're going to locally store all of the agents they've interacted with and their sync values. So here, when agent 4 and 7 interact, they're going to share the sync value 1, 3, 2. And they locally have this tree of all the agents they've seen so far. And they're going to add the ID of the agent they met. So agent 4 knows that they met 7 with sync value 1, 3, 2. And conversely, 7 met 4 with 1, 3, 2. Now what happens when agent 7 meets the other agent with name 4, they know that there's a collision because this agent 4 does not have the matching sync value. So we can indirectly check collisions with a consistency check. So agent 7 realizes, hey, I've met agent 4 and we shared this sync value. So this agent now should have the same sync value, but it doesn't. So that's how we indirectly detect a collision and now can trigger the reset. Now, crucially, this sync mechanism has a safety property that once we have unique names, all of the matching sync values will be preserved. So there'll never be any false collisions, and that will let us actually stabilize in the good setting when we have unique names. Now, our full protocol pushes this idea forward to get it to be all the way to taking log n time. So rather than just having sync values of direct interactions they've had, we're going to store a sync value history in a depth H tree. So if we have just a single interaction, sort of to begin the protocol, we would store the same thing, where agents 4 and 7 would remember that they met each other with a sync value 1, 3, 2. But now the idea is that we're going to have the information go multiple levels deep. So we would like to remember more indirect causal chains of sync values. So now let's say agent 7 meets agent 2, and agent 2 also has a similar sync tree. The first thing they do in their interaction is they're going to end up sharing their entire tree. So they share all of their values. So now agent 7 and agent 2 are going to, again, share the sync value with each other, but now they're going to have a longer tree. So from agent 7 perspective, it says, hey, I interact with agent 2. We shared the sync value 99, but then agent 2 had interacted with 3 and 8 and shared these sync values. This is going to let us more indirectly detect name collisions. So now our total tree is going to have some depth h, and what that lets us do is that lets us check consistency of causal paths that now have a longer length up to h. And what it turns out that we'll need is we'll need this length of the path we're going to detect and the depth of the tree are going to have to be of the order log n. And the reason for that is a signal that starts from one agent 4 and reaches the other agent 4 by epidemic, that signal would have length of the order of log n. And that epidemic process would reach from one to the other in order log n time. So we actually know that in optimal log n time, there's going to be some causal chain of length n between one agent and the duplicate agent. So we're going to use these causal chains to detect a collision in a similar way. So now agent 6 eventually interacts with agent 4. And because their tree is of depth log n, their tree goes deep enough that they're storing this entire causal chain all the way back to this agent 4. So agent 6 knows, hey, I've seen agent 4 before. And so when agent 6 meets agent 4, they're going to take this causal chain and they're going to check for consistency, check that agent 4 has some matching data. And in this case, there's no matching sync values, so we detect a collision. Now, crucially, this idea still has a safety property, that when you have unique names, there's no false collisions. As an example of that safety property, if agent 4 and agent 7 met again and changed their sync value, they would update their data, and now they would have a new sync value stored from each other. Now let's suppose this agent 4, which has a different sync value, now meets with agent 6. Well, the bottom interaction, agent 6, knows they interact with agent 4 and they had sync value 1, 3, 2, but that information is now outdated because agent 4 met agent 7 again and had a new sync value. So this will not end up being a false collision, though, because we go multiple steps deep. So rather than this interaction, we're going to keep walking up and down this path. And here we find that there's some interaction that needs to be shared by both causal histories. In this case, the 2-7 interaction appears in both chains. So we do have the matching sync value 99. And that matching sync value means we're not going to say this is a collision. So in summary, we have a time and space optimal silent protocol, and we have a time optimal non-silent protocol. Now, crucially, this non-silent protocol uses exponential space for two reasons. One was this sync value tree that we just showed, but also the rosters themselves. The way we share the names also needs exponential space. And it remains an open question if there's any self-stabilizing leader election protocol which uses sublinear time and sub-exponential space. Another interesting open question is to consider this ranking problem that we solved from the initialized setting. Perhaps it's possible to solve ranking in an initialized setting with sub-exponential space, again, in optimal time. And thank you for your attention, and please see the full paper for more details.